Okay, so this is our formal lab 2 lab report on resistive forces. So we explored the idea of air drag, and we investigated the relationship between two balloons of different sizes falling through the air, which led us to develop a research question of how does object size impact air drag and thus the ability of a balloon to reach terminal velocity. So our objective was for the balloons to eventually reach a terminal velocity. This occurs when the resistive force upwards equals the gravitational force downwards. So thus the object has no acceleration, net force is 0, and velocity is constant. We also have Newton's second law of motion happening here. And we see that when objects move through a fluid, they feel a resistance due to the fact that it's dragging the fluid with it and also pushing the fluid in front of it. So the object has to exert a force on the molecules of fluid in the direction of motion. So with Newton's third law, the fluid molecules exert a force back on the object, which opposes direction of motion. And this is the equation that we used for inertial drag.
For models of physics, we had two models, so a free body force diagram to visualize all the forces acting on the balloons. So both of them will experience same forces acting in them, considering they're made of the same material and are dropped at the same height with the same initial velocity. But the amount of force each experiences differs based on their size, considering the green is bigger and heavier and the blue is smaller and lighter. And then this is our system schema, which are identical for both balloons.
For our experimental design, we were looking at two balloons dropping from a fixed distance above the ground. And our key variables, we're looking at the radius of the balloons, the mass of the balloons, gravity, and drag force. The radius of the two balloons was the smaller balloon having a 7.003 centimeter radius and the larger balloon having a 13.051 centimeter radius. And then the two differing masses of the balloons with a 2.58 gram mass and a 2.82 gram mass. Those were the two variables that were changed. The green is the larger balloon, the blue is the smaller balloon, and we reduced error in our experimental design by repeating the experiment 8 total trials per each balloon.
So this is a visual representation of our experiment, and for our trial setup, we dropped each balloon at a distance of 2.92 meters. And then this is an example of our first trial graphs. The left is the blue and the right is the green. And as you can see, there's a constant decrease slope for position and also a constant decrease in velocity. And then this is just another example of graphs. This is for trial 2. And then you can note that, for example, on the left graph for the blue balloon's velocity, the terminal velocity starts at around 1.6 seconds and lasts until 2.8 seconds.
Okay, on this slide, you can see the data that we got from Tracker. So we have the time of the drop from beginning to end, the distance that each balloon was dropped from, and the velocity and acceleration of each trial. This is trials 1 through 4 on this slide. And then 7 through 8 can be seen on the next. 5 through 8 can be seen on the next slide. And then looking at our data from Tracker, we can verbalize this data by saying that the green balloon takes a longer amount of time to reach the ground compared to the blue balloon. And both of them were dropped at the same change in y every trial. The velocity had the blue balloon as a greater value compared to the green balloon, and the acceleration, the blue balloon had a greater acceleration compared to the green balloon. Both balloons were able to reach terminal velocity at some point during all of these trials, whether that was visible or not, based on each graph.
So in terms of our data analysis, we calculated that the average terminal velocity for the blue balloon was about negative 1.71 with the standard deviation, and the green with about being negative 0.86 with standard deviation. And so we found that the smaller radius balloon, which was the blue balloon, ended up having a greater terminal velocity than the larger radius balloon due to air resistance based on its size. And so in order to calculate the drag coefficient, we first had to find value of the inertial drag force, which if we are looking at when an object is experiencing terminal velocity, this is equal to the gravitational force. So we calculated the gravitational forces. And then using this equation over here, we were able to calculate a sea drag force and for the blue balloon and a sea drag force for the green balloon.
For our scientific reasoning of our experiment, we are most concerned with the data that we got and how we can correlate that to the physics concepts of our research question. So the data from Tracker support that the balloon with the greatest terminal velocity reached the ground faster. And both balloons reached terminal velocity in the trial, so size did not impact the ability of the balloons to reach terminal velocity, just the value at which that terminal velocity was reached. And furthermore, we found through finding the air drag that the green balloon had a larger air drag since the resistance is larger due to its larger size.
After completing our experiment, we did compare our data to the code that we used to represent our experiment. There were some inconsistencies in this code when representing our experiment through the code. The time points at which the code had the drop shown was much faster than the actual drop of the balloons in our trials. They were off by a scale factor of 100. The graphs from the code also did not match. Well, they matched the expected trend of the terminal velocity, but they were not explicitly shown on the graphs in our trials. So they weren't completely matched up, but showed the general idea. The graphs in the code were also less exaggerated than our predicted graphs. In an attempt to minimize error, we made sure that the same person completed each task. So we had the same person drop the balloon in all of our trials, and we made sure that the people that were analyzing Tracker were the same for all trials, just to keep everything consistent. We attempted to drop the balloons from the same height each time, and we repeated our procedure multiple times and recorded the standard deviation to minimize our error. An element that may have been left out was remeasuring the exact point that we dropped the balloon at instead of eyeballing it each time, instead of measuring with our meter stick each time, the 2.292 meters. Our sources of error were that some of the trials did not show a perfect point of terminal velocity. The pass of the balloon also could not always be guaranteed because sometimes the balloon did not fall in an exact straight point down. Tracker also had some minor glitches while tracking the fall of the balloons, and having someone track something will not always be 100% accurate.
These were the uncertainties that Tracker gave us for each of the different balloons, looking at velocity and acceleration for each of the trials. We really wanted to repeat these trials as many times as possible just to minimize that overall error that we were going to experience.
In conclusion, we found that the balloon with the smaller radius reached a greater terminal velocity. However, we did manage to get both balloons to reach terminal velocity, but the blue balloon did take less time. The time it took for each balloon to reach the ground, as an example from trial 1, the blue balloon took 3.6 seconds and the green balloon took 4.5. And then these are the average terminal velocities. And as you can see, the blue balloon did have a greater terminal velocity. And air drag was seen to impact the velocities of both balloons, but impacted the larger balloon the most, which is indicated by its slower terminal velocity. And there was little difference in gravitational force from the two different masses, considering that they were both pretty similar. And for drag force and drag coefficient, the blue balloon had a smaller drag force and a smaller drag coefficient, and the green balloon had a larger drag force and a larger drag coefficient.